start today's IBiM talk. So today we are very honored to invite Dr. Wu Wen to give a presentation on the roughness effects in non-equilibrium turbulence flows. So Dr. Wu Wen is essentially get his PhD degree from the University of Queen's University under the supervision of Dr. Ugo Piamelli. After that, he go to the Johns Hopkins to continue his postdoc research. In 2020, he got an assistant professor position from the University of Mississippi. And in the summer of 2022 and 2023, Dr. Wu Wen served as a visiting assistant professor at the Center for Turbulence Research at Stanford. So Dr. Wu Wen's research is mainly focused on the roughness interactions in the turbulence flows and the vortex-dominated flow and flow separations. So I'll left the platform to Dr. Wu Wen.
Okay, thank you, Dr. Zhang, for the introduction. It's a great pleasure to be invited for this talk and share with you some of our some of the insights that we obtained through the past few years on roughness effects. I talk with Dr. Zhang. It seems that the topic is slightly deviate from the nominal concepts that IBiM is focusing on, but hopefully it can give you some insights about roughness. The work that I present here has been funded by NSERC, Hydro-Quebec, Air Force Office of Scientific Research, and NSF. I will try to answer the questions by the end of the talk, but let's see how it works. So for those of you who are not familiar with roughness, that's one important thing is it's everywhere in our daily life. Here I listed only a few examples that encounters in engineering applications. So it covers the industrial sectors like civil engineering, where pipes are widely used, and aviation industry, where we have this icing problem that many people are trying to tackle right now, and also for geological engineering, where the topology of the atmospheric boundary layer matters as a surface microstructure. And actually, besides those apparent rough structure, at high Reynolds number, all surfaces are rough. I guess everyone is quite familiar with this Moody diagram. One thing that I want to point to is how small this relative roughness is. As you can see, at high Reynolds number, even a roughness that is a small fraction of the hydraulic diameter of the pipe can significantly affect the friction factor. A quick estimation we can do is for water that is passing through a pipe that is 0.5 meter, a very small rust that is maybe 0.5 millimeter give us a Reynolds number. If the velocity is 1 meter per second, we're roughly at the Reynolds number 10 to the power of 5 or 10 to the power of 6. And even a very small, very small, tiny rust can increase the drag by maybe 50%. So that's why we have been focusing on roughness, and there's a trend on looking at their effects. And also it's because, you know, computational capability is increasing, so we can resolve it with ADDIE resolved technologies. So the work that we have been working on during my PhD postdoc and AP period includes several non-equilibrium effects, which means the flow is not a canonical boundary layer anymore. I put this in two categories. On one hand, we look at the cause of the external force or non-equilibrium, which includes flow separation and vortex-dominated flow, system flow with a rotation, and also pulsatile flow. On the other hand, we have been looking at different surface structures, including homogeneous sand grain, heterogeneous structures like vortex generator and also Bayer-inspired structures. Today, I'm going to focus on three non-equilibrium effects: the adverse pressure gradient, aka flow separation, and Coriolis force in a rotating system, and pulsatile flows. This work, for all of this work, I have the privilege to work with a group of fantastic scholars, including Dr. Piumati, Dr. Yuan at Michigan State University, Dr. Bani Asadi, and my students at the University of Mississippi. So a very broad review of the roughness effects. What does it do to turbulence? There are extensive study, and you can see more details in Jimenez and Chang's reviews. But I would like to point to a few important factors here in this talk. First of all, roughness, as we all think, it causes additional drag because it's protrude from the surface into the flow. And what people have observed is it causes more homogeneous turbulence, but in terms of the engineering point of view, what is important is how we predict it. So luckily that the profile that we used for smooth wall still applies to some extent for a rough wall flow. So basically it still follows this log law under the inner units, but there's a downshift as shown by this red arrow. So the markers are different roughness, and you can see there's a downshift in the log law, but still we have this 1/kappa slope. And that's why people can derive this modified or this law of the wall with roughness corrections. And these two have been used in different fields, but basically they are equivalent. And as you can see, there are a few parameters. The first, you have to shift your wall normal distance by a certain amount, which is d, which is called the zero plane displacement, or you can think it as the wall offset. The roughness is shifting the wall a little bit further away from the surface. And then there's this important parameter either called Y0 or in some field called KS, which is called equivalent Sandgren roughness, which is like a length scale that is used to characterize all the lengths in the roughness layer. And this downshift in the log law can be derived as a function of the roughness height based on some fantastic correlations that people have been used and verified. So basically, then the job is just to find, okay, what are the D, Y0 or KS for each rough wall? Can we identify them for different type of roughness based on their geometric parameters? There are numerous studies on this, fantastic work. And if you're interested, please refer to those two reviews. So what does our reduced order model do is exactly the same. The first is you have to shift the region of your wall from the real surface to a virtual origin. So you basically bypass a region in the rough sublayer. And then there are some strategies like increase the added viscosity and reduce damping. But eventually, the important factor is Y0 or KS. Here's a table summarizing some roughness corrections has been used in different RANS models. So they're pretty standard. But what I want to emphasize and what I'm going to use to explain what we observed is a wake field. It's very straightforward. Wake field is just what is going around each rough element. So as you can imagine, it depends on the geometry of the roughness. If I'm standing in an atmospheric flow, the wake behind me is going to be different from the wake behind the car. That's apparent. And it has been used as a way to decompose the fluctuation that is generated in the flow. So as you can see, these are geometry dependent spatial fluctuations, not like the stochastic turbulent fluctuations. So isolate these two is a very important step to study their effects. So basically, if you start from a Reynolds decomposition and you get this mean flow field and stochastic fluctuations, then you can apply a spatial average such that you have an average over the entire plane and a spatial variation behind each of these elements. Again, for example, me and the car is all exposed to a 5 meter per second flow, but the wake behind me and the car could have a difference. Maybe the velocity behind me is 1 meter per second slower, but the velocity behind the car could be like 5 meters per second lower than the average. The spatial discrepancy is what have been used to describe the effects of roughness. And also, you need to define the roughness sublayer, which is the region where if you go beyond that, you have that law of the wall that is called Towson's similarity, which enable us to find the wall shear stress. I do want to emphasize that it's not an easy task to find the total drag in a rough wall surface. For smooth wall, you just get the velocity gradient at the wall and you get the shear stress. But for rough wall, you have the form drag, and usually it's very hard to measure the form drag around each small rough elements. So what people do is, okay, we assume that this law is still valid. Okay, so basically you assume this D, and then you try to fit your velocity such that it shows the slope of 1 over kappa. So in this plot, it's just a toy problem. I assume a velocity profile, and I'm changing this factor F, or you can think I'm trying to estimate the actual util such that I do have a slope that is in line with this black line. As you can see, by changing this factor F, this red line best fit the log law. Okay, it's just because when you adjust this parameter in this profile, it shows that slope. So basically, there are two assumptions. The first is you know what is D. Okay, if you don't know what is D, the fit is more complex and there's more uncertainty. And then you're assuming that log law remain valid. So I'm trying to find this 1 over kappa slope. And the log law is not affected by the roughness. So basically there's many strong assumptions, but this is usually what people do to get the total drag on a rough wall. Apparently, all this strongly depends on the nature of the flow. If you have a canonical turbulent boundary layer in equilibrium, then they are valid. What we have been working on, and I would like to share with you today, is what if we don't even have an equilibrium turbulent boundary layer? Okay, then this matter is going to be in question. What if my velocity does not have a log law at all? Then how are we going to do all this analysis? Some people may say, okay, if the turbulent boundary layer is in equilibrium, we know that the Reynolds shear stress away from the wall can be used to estimate the wall stress, and that's what people do. But again, the assumption is the boundary layer is in equilibrium, and that's something that we try to challenging, and hopefully I can convince you that this is not the case, and we are facing some big problem in our daily life. So in our daily predictions. So the first topic that I want to share is flow separation over roughness. Flow separation, as we all know, it has been utilized in golf balls to induce transition such that flow separation can be delayed. This is the canonical aerodynamics class example. But what if the flow is already turbulent and this transition has already been bypassed? So if roughness, we all think roughness can further enhance mixing. So does this additional mixing delay or reduce separation? If it's enhancing mixing, you can bring more high momentum to the wall, and hopefully it can reduce separation. So that's the question that we're trying to ask. What we do is we utilize a configuration that is suction and blowing to mimic the flow separation over a surface that is not does not have a strong surface curvature. We do this for two reasons. The first is we focus on aero aviation applications at the beginning, and the second is the suction and blowing can isolate the streamline curvature effects, like bump or something, so as we can be more certain about what are the effects of roughness. And a few effects that people have observed for adverse pressure gradient induced flow separation in canonical smooth wall turbulent boundary layer includes the amplification of the wake region. This wake, I want to emphasize, is not the roughness wake flow, but the wake region in the law of the wall in the outer layer is amplified. And also there's the outer peak of the Reynolds stress. These are pretty common observations. Then the question, as I said, is what if we have adverse pressure gradient and roughness? In such case, as I will show you, even the definition of separation is not really clear. So what we did is a wall resolved large eddy simulation with sand grain roughness covers the bottom wall of this boundary layer. So this is a canonical boundary layer setup. You have a turbulent inflow generating mechanism, recycling and rescaling, and we start the separation. We apply a suction and blowing on top of the surface and gonna create a separation bubble on the bottom of this wall. So we use virtual sandpaper that consists of randomly distributed ellipsoid, and they are represented by an immersed boundary based on the volume of fluid approach developed by Scotty and Yuan and Piumani. I want to emphasize that at the Reynolds number that we studied, this roughness is considered as fully rough, which means the law that I show you, the downshift of the log law is valid at this Reynolds number. And here I'm showing that the volume fraction of the fluid, giving you an idea of, okay, how dense are the solid. So basically 1 is purely fluid, and 0 is purely solid. So that's how the porosity or volume fraction of fluid looks like. The roughness height is chosen to be 4% of the boundary layer thickness. So we try to minimize the blockage. One magic number that I want the audience to keep in mind during this talk is this roughness gives an equilibrium sand grain roughness height to be 94. So if you use the RAS model, you're going to use this magic number 94 for this roughness. Okay, I'm going to show you that in different cases, this is not true. And if you use this 94 in your model, there's going to be uncertainty. Okay. So what we observed is, compared with the smooth wall case, this is the mean flow, and these are some streamlines. Clearly, the separation bubble is much bigger for the rough wall. This is not the first time that people observe flow separation is enhanced by roughness, but there's also people saying that flow separation is reduced by roughness. Our configuration supports the first type of conclusion. The separation is more prominent than the smooth wall. It means that additional mixing by roughness is not doing good. There must be something else that caused the flow to separate more. But instead of talking about why it caused the flow separation or largest flow separation, I want to emphasize on the physical, application meaning of this flow. So as I said, this KS plus is important for if you use a model. So how does that look like in this flow? So what we do is, okay, that's what people do. You get the smooth wall profile, you get the comparable rough wall profile, and you compare them at same location. This is at 0 up to 75. As you can see, I'm not even look at the separation regions, only where the adverse pressure gradient starts to kick in and affect the flow. At x equals to 0, you still see these two profiles are parallel. Okay, the rough wall is still have like a 1/kappa slope, and we can measure this downshift to get a KS plus. Okay, and what we get is this KS plus is around 190 or 160, 170, something like that. And if you measure it all the way down to 64, you can see it is decreasing, but now this number is close to 94. Okay, that's the magic number for equilibrium flow. So it means that if you use 94, then you're underestimating KS plus in this flow, even before flow separation, where it seems to be still an attached boundary layer. So that means adverse pressure gradient cause uncertainty, cause some deviation from the calibration that we used in equilibrium wall model. But what is more important is if you go more further downstream, where the adverse pressure gradient is stronger and stronger, you see for at this location, well, there's still kind of like a 1/kappa slope. If you move further downstream, what people observed is the wake region is enhanced, and then you start to question, okay, is there really a 1/kappa slope region in log law, and how are we going to measure the downshift? And by 75 is here. It's not anywhere close to the separation region. Measuring that 1/kappa, identifying that 1/kappa region starts to get really hard. And if you do try plot this try to get the slope of this profile, you'll see that 1/kappa region is really hard to be identified. And this is not at very low Reynolds number. If this is an equilibrium boundary layer, you can see a definitely a well-defined 1/kappa region. The reason that it is not showing here is basically because of the adverse pressure gradient. So quickly, the equilibrium loss becomes invalid, and we cannot do this anymore further because it's not log law anymore. So all of this theory does not hold anymore. But the user of the CFD doesn't know this. They just assume that this is log law, and we use KS equals to 94, which both underestimate the roughness effects, and you're assuming a wrong velocity profile. So that's what we observed. Another important message for engineers is, okay, how we define flow separation, right? Flow separation, if you look at the phenomena, it is like the detach of the flow from the surface. Detach means it leaves the flow. So basically at the point of detachment, you have a 90-degree angle of the flow with respect to the wall that is based on the continuity equation. If your U becomes 0, V has to be positive. So a 90-degree streamline. So that's one criteria. And of course, I mean, flow separation usually it's accompanied by a reverse flow. So people use U equals to 0 as the threshold. There are some other criteria, like 50% of the time the instantaneous flow over the surface is reversed, or CF equals to 0. More reduced order first principle criteria is the shift factor is greater than 1.8 to 2.5. So what I'm marking here is the location of a few of the thresholds in the smooth wall and over a rough wall. So as you can see, and this is another additional plot, basically the lines shows the flow angle and different markers represent different separation criteria. This is for the smooth wall and this is for the rough wall. What you can see is all this criteria agrees with each other for the smooth wall. So if you use any of them to predict when does the flow separation occurs, you pretty much give a reliable prediction. But for rough wall, it's not. Okay, different criteria can give you different prediction of the flow separation point, especially this. Let me see, the green triangle, red circle, or CF equals to 0, and also 50% of the time the instantaneous flow is reversed. Okay. And this I measured on top of at the crest of the roughness. It's not below the roughness. And this is because before your mean flow detaches, the flow inside the roughness layer is already reversed and give you a negative CF and also more reversed instantaneous flow. So if you use this as your criteria, if you're doing experiments or simulations and you say, okay, CF equals to 0 is flow separation, you're going to predict an earlier separation. And that is not a small uncertainty. You basically have an arrow that is maybe 10 boundary layers thickness upstream. And that is simply because the flow, the wake flow in the subnet, in the roughness sublayer that changes the CF and local flow behavior. And we have some analysis regarding how TKE is changed. We found that the shear production of TKE is significantly enhanced, additional mixing. But why it doesn't prevent flow separation, as we figured, is the roughness actually also introduce a mean flow momentum deficit. Means that near the wall your mean flow is slower, so it's less, it's more likely to be slowed down and cause flow separation. So the additional mixing does not compensate this momentum deficit. I won't talk about these details, but it's interesting analysis on how turbulence is generated in this flow. So the take-home message is for this is, if you use the canonical equilibrium law to predict this flow, there's going to be uncertainty, quite significant uncertainty, and you're going to predict flow separation with less confidence. So the second type of non-equilibrium phenomena is pulsatile flow. Okay, we always assume if you teach aerodynamics or fluid mechanics, the first thing that we do is assume that something is travel at u infinity equals to A, B, and C. Okay, it's a constant value. I mean, that's where we all start as theory, but in real life, a constant ambient flow is rare. I'm not talking about there's a passing vortex that causes unsteadiness. I'm talking about the driving force of the flow is unsteady. For example, a shark or a fish that is propelling itself, it basically generates a wave-like rhythm that creates the unsteady driving force. And atmospheric flow is never steady. There's always wind breeze. Even for a vehicle that is driving, it's not at a constant speed, right? If you use cruise, that's the best approximation, but there's always, for ship, there's wave-induced unsteadiness that you feel this bumpy motion. And even for pipe flow, we usually assume, okay, the pipe flow is flowing at a certain meter per second. But if you look at these pumps deliver the fluid chamber by chamber. And there's always this position of pressure that is unavoidable. So similar to roughness versus smooth, pulsatile flow is, I would say, the nature of the flow instead of like a special case. The unpulsatile flow is an oversimplified special case that we have been utilized. Especially another thing is there's a risk I mean, there are many phenomena that the mean flow cannot sufficiently predict. One research that we've done is the suspension of particles by this impinging vortex. And we come to the conclusion that the mean wall shear stress and the transient instantaneous shear stress shown by this black line are so different that they can cause fundamental difference in the momentum and mass transfer on the wall. For example, if you have a particle on the wall, if you use the mean CF, it will not be picked up at all because it average out these peaks. And actually the strong instantaneous peak can actually lift it. So if the mean flow is not sufficient to predict the actual physics. So we want to look at pulsatile flow over roughness. This is much less studied than pulsatile flow over smooth surface. But each of this topic, roughness and position, they have been studied extensively. For the position, roughness, we already talked about it at the very beginning. For the position over smooth wall, I would like to have a very brief introduction about this. It's basically, if you think it in the other way, that the fluid is not moving, but the wall is moving. So relative motion is basically a Stokes second problem. And you're gonna have a Stokes layer near the surface. This means this represents the velocity. So what it eventually looks like is away from the wall, you basically have a plug flow. Okay, it's basically a plug flow at the magnitude of your oscillation. But near the wall, you have a Stokes layer that have more interesting behavior. It's not like a rigid shift of the profile, but you have more interesting physics. These are velocity profiles at different phases. So people have defined the Stokes layer, which is whose thickness is related to the frequency. The lower the frequency, the more thicker the Stokes layer is. Okay, and there has been extensive study on smooth wall oscillating flow, and people are come to the conclusion that if the frequency is low, basically you can assume instantaneous equilibrium, means that you can use instantaneous wall shear stress to and the canonical equilibrium boundary layer theory to predict the flow, which makes sense. I mean, to the lower end, if the frequency is very low, the turbulence has time to adjust to its current status, so we can use instantaneous equilibrium to describe it. On the other hand, if it's very high frequency, then the Stokes solution that we can get can be used to characterize the wall shear stress and near wall flow. But in the middle, this is very low and very high frequency. Anywhere in the middle, there are still debates. Okay, even for position over smooth surface. Then my concern is, what if the roughness works with the Stokes layer? There has been some studies, especially in the geophysical context, like ocean geography specialist, and people have been, again, focusing on identify the roughness length scale and try to use this law. And we already show you one example that this law is not valid anymore. And in the turbulence community, there has been some fantastic work working on simulating pulsatile flow over roughness. But we think there's still more work to be done. And their conclusion is basically the same as the smooth wall. One additional observation is roughness is enhanced at low frequency. So this is still largely unexplored. And the reason is, this is the pulsatile flow diagram. For roughness, you have a roughness and a roughness sublayer that is roughly 3 to 5K. Then our question is, the limitation is the low Reynolds number and lack of discussion on the Stokes layer. But our question is, if you have roughness and Stokes layer, they are all in the vicinity of the wall. they're basically in the same region, two mechanisms. Which one's dominant? Do they overlap or they are stacked on one on top of each other? Okay, is the Stochastic layer on top of roughness or roughness layers on top of Stochastic? And how do they change each other? And the most important question is, if you use equilibrium, the roughness correction derived from the equilibrium flow, can you predict this at least from the main sense? So that's something that we try to understand, okay, when both are present in the flow. So what we did is the DNS of positive flow over sand-grain roughness. The driving force of the flow, as you can see, is following a periodic cosinusoidal form. And we choose to have a position that is about 22% of the mean flow at very high Reynolds number, such that we have a better scale separation. And we tested 3 frequencies. They correspond to 3 Stochastic layer height. Okay, as I mentioned, the lower the frequency, the thicker the Stochastic layer, and we are expecting, we are looking forward to see, okay, how does the Stochastic layer change by the roughness? So an instantaneous flow looks like that. It's a pretty heavy simulation with almost 1 billion grid points with the roughness layer resolved. This is how the flow looks like. The flow pulses, oscillates, and you can see there's interesting things happens around the roughness, which are these white patches. Okay. One thing that I do want to mention is our high Reynolds number enables sufficient, I mean, not sufficient, but good scale separation. So the small roughness makes the roughness sublayer to be limited to maybe 100 to 150. Well, we all know the logarithmic layer is about 0.1 to 0.2 boundary layer thickness, so that's 5 plus about 200. That leaves us not very big, but maybe in wall units, 50 wall units in between that could be a log region or a Stochastic layer, but at least they are not overlapped. Okay, if it's low Reynolds number, then your roughness sublayer is already covering the entire logarithmic law, and the scale mixing is blocking the true physics. That's what we saw as one downside of existing studies. Now we have a clear separation for these 2 layers to play around. So what we observed, again, I'm focusing on KS plus, that magic number 94. Okay. We studied 3 cases. As you can see, this is the downshift that you can measure with comparison with also positive flow at these frequencies, but it's a smooth wall. The difference, you may say, is not that large, but when you calculate the KS plus, the equilibrium roughness height, it increased from 94 to 98 and eventually to 133 when the oscillating frequency increases. This is more like 30% increase. Okay, it means that the good thing is we do have this 1 over kappa slope, means that, okay, it's not that non-equilibrium, but if you still use 94 to predict this flow, then you're underestimating the roughness by 30%. The good thing about our simulation is we can directly measure the U-tau, so you don't need any fitting procedure that can introduce the uncertainty as I introduced. Our measurement of the total drag is reliable. So basically we're saying the roughness is increased by oscillation. That's what people observed as well. And then we try to see, okay, does the Stochastic layer still exist? Is it on top of the roughness sublayer or not? This result basically saying the roughness scaling law is still dominant. It means that we should use the roughness law to describe this flow. But the question then is the Stochastic layer still there? Okay, is it still somewhere in that flow? And what we observe is, yes, the Stochastic layer is still there. It's just displaced by the roughness sublayer. And in the main well, it is thickened. So what it's showing here is this is the smooth wall profile, and the wall normal distance is normalized by the Stochastic layer thickness. So first of all, it is shifted, displaced by a certain portion of roughness height, and it's not monotonic for some reason that we are, it's monotonic, but we don't know why. It's a small fraction of the roughness height. And then it is thickened. Okay, the Stochastic layer used to be just 2 ls, but now it's roughly 8 to 10 ls, characterized by the pulsating flow. So it means the Stochastic layer is still there. It's sitting on top of the roughness sublayer, and it is thickened. That is what we observed in this flow. And then if we want to study the turbulence, we look at the fluctuations in the roughness canopy. This is an instantaneous movie showing that the flow is changing between a cycle quite significantly. And I want to remind you that our flow is always one direction. It's always from left to right, but it has a faster and slower phase. It's never actually, the main flow never reversed. But within the roughness canopy, you can see in some time instant is all blue, which means the flow is all reversed. So what we do is, in order to analyze this, the triple decomposition that people have used in previous study is not sufficient, because we have a periodicity or an imposed variation due to the position. So people always use temporal triple decomposition to isolate the motion at that frequency. And then what we really need is to apply a spatial average that to isolate the roughness-induced spatial variation and the position-induced temporal variation. So this is what we call the quintuple decomposition that we proposed. It is slightly better than what people have used that is not based on a rigorous mass. So basically, you decompose this instantaneous total velocity into a long time average, the spatial variation of the long time average, and then this is the phase variation because of this temporal variation, and then the local spatial variation of the periodic position and the stochastic one. So we're trying to decompose it in that way. And we look at each of the stress. What I'm showing here is the streamwise fluctuations. This black circle is rough wall, no oscillation. And the lines are rough wall with oscillation. This is the Reynolds stress. What I want to emphasize here is, as you can see, compare with the non-oscillating, non-pulsating one, the Reynolds stress is significantly increased. But what people use to describe the roughness effects, which is by the mean wake, which means if I stand in the wind, in the long time sense, what is the recirculation region behind me? It doesn't really change by the position. What is changing is the pulsating wake behind me when the wind is breathing. And we believe that is the cause of this increased Reynolds stress, because the mean wake doesn't change. Is when the flow past me, how the vortex shedding instantly behind me that changes this Reynolds stress. So this term has been long ignored in previous studies, and we are able to identify that it is the cause of the increased Reynolds stress. So that's the second topic. I think I'm running late, so I'm going to be brief on the last one. Is roughness in rotating systems. Rotating system is, again, what we always often encounter in engineering and nature science. For example, turbo machinery, these are hydro turbines or gas turbines that you have the surface roughness due to accumulation of rust or biomass, and we're expecting that this is not good, right? But what is hard for study this problem is you have to put your entire wind tunnel on a rotating floor. And that is hard. I mean, if it's a small scale, like what these people are using is about 8-10 meters, they put it on a rotating floor, everything, the pump, the wind tunnel, and they rotate it to create this rotation. But for wind tunnel of this size, rotating it is not feasible. So we decide to use simulations to do this because basically we can easily introduce the body force. And there has been some studies in terms of rotating turbulent shear flows, but not on roughness. So a quick review on the roughness, the rotating effects is you have this additional term in the Navier-Stokes equation, it's the Coriolis force. And this rotation is about the rotation x is in the span-wise direction. So if this is the channel with two walls, the flow is basically spinning in the plane that is showing. Here I'm showing the rotation that is this direction. It means the entire channel is rotating like that, similar to the turbo machine. So basically the mean flow field is not symmetric about the center line anymore. I don't have time to explain this, but what people have observed is there are two sides of the channel. If the rotation is in this direction, as I'm showing here, on one side is called the unstable side, the turbulence is enhanced. While on the other side, the turbulence is diminished, and you sometimes can have a quasi-laminar flow. It's basically due to the stability mechanism of the Coriolis force. So in short, you just keep in mind, we'll study a direction of rotation like that. The bottom wall is unstable. You are expecting the turbulence to be augmented. On the top wall, you are expecting the turbulence to be decreased. And at high rotation rate, this effect is amplified such that you could have a laminar flow on the opposite side. So then the question is, roughness introduce additional mixing. If on the unstable side, the Coriolis force tries to stabilize the flow and laminarize it, then what if we have roughness over there? It's like counteracting. So how do these opposite effects interact, especially near the stable side? And we are also interested to see how roughness change the flow on the unstable side as well. So what we did is, again, DNS of channel flow at Reynolds number 500 to 1,000. And we have cases for comparison, the smooth wall and rough wall, and they are all oscillating in this way. This is the instantaneous flow shot of a smooth wall case, where you can see the bottom wall, the roughness, the streaks of the turbulence is enhanced. And on the top wall, you have a quasi-laminar case with isolated turbulence spots. Again, we are choosing 4% of channel half height as roughness height. So that magic number, the equivalent sand grain roughness is around 94 or 100. And we're gonna see that is not really true when there's rotation. So this is how the velocity profile looks like. There are a lot of lines, but the general message is, again, you're trying to measure the downshift of the log law. Luckily, it seems that there's still this log law, and you can measure a downshift by comparing the smooth wall and rough wall cases. But the KS plus is not 94 anymore. If it's not rotating, it's 94. If the rotation rate is intermediate, it's 57. If it's high rotation rate, it's 21. Again, this shows the risk of utilizing canonical boundary layer observation in our predictive tools for non-equilibrium flow. And then the Townsend similarity hypothesis basically saying that the roughness only affects the near wall region and the outer quantities are not changed in wall units, but that is not true, especially on the stable side. So what you can see here, the blue line is the highest rotation rate, the black line is non-rotating, and the red line is the intermediate rotation rate. As I point out, at high rotation rate, basically on the stable side, the turbulence is decreased. It does not have this peak anymore. And if you look at WW and VV, it's almost completely zero, right? But the existence of roughness boosts the mixing over there and kind of like destabilize the flow and prevents it to become fully laminar. I mean, that's intuitively correct. So our conclusion is on the unstable side, the Townsend similarity hypothesis is still valid. It means if you use current tool to predict it, you roughly get a good idea. But that is only for U prime. For V prime and W prime, even if you use the current tool to predict it, it's not really a good prediction. And on the unstable side, there's no similarity at all. The fundamental trend is different. We have more analysis, but due to the limit of time, I won't talk about that. But the basic idea is the wake, that is the local circulation behind each of the roughness elements, is the cause of this change. So in summary, I've shown you 3 examples, and we are saying that the effective roughness height is unpredictable in realistic turbulence, unpredictable based on current understanding. And if you use the equilibrium relation, then there's going to be uncertainty. The outer layer similarity means the validation of the log law may hold in some cases, but it's very likely, it's very easy to get deviation from that. And I hope I convinced you that the wake, the local spatial variation behind each roughness elements is the key to characterize the roughness effect, especially if it's not equilibrium. So that's all. Thank you, and I'd like to take questions.
Many thanks for Wenwu's talk. It's actually like fundamental, but sort of systematically investigates roughness, like interacts with TBLs. So you can just open your mic, or you can left question in the chat, as we already did. So, like so I have a question, like say, like we like it's sort of not like 100% pertinent to your talk, but like like we like discuss my research, like say, I have like very tiny vortex generators. It's sort of like a roughness. So for right now, what I measured in the water tunnel is like the TBL I theta is like 1,000. And my roughness height is like y plus equal around 20. So for that kind of like we suppose it's like we did observe the drag reduction in the wind tunnel test. And we suppose it's like this tiny roughness is sort of like organized, or it's sort of like reduced like the large vortex in the inner boundary layer. So like say, what's your opinion on that? Because we never did like a LES simulation, or we never did like a 3D measurements on the inner boundary layer. Although that's my plan, but like I say, what do you expect from like if we do the like, for instance, the Shakes box measurement in the inner boundary layer? What should I like, especially like, or like how should I like post process the inner boundary layer data?
Okay. That's a great question. I think, as I emphasized here, you want to look at the wake field. So the variation of turbulence statistics due to the shape of your geometry. this drag reduction geometry, as we all know, riblets is one of them. And what Dr. Amirida Ruhi has presented at this seminar is an example of that. Based on what you described, your RE theta is 1,000, and your, can you remind me what is about
the height
20?
of the MVG is like 1 plus into 20.
Okay, so RE theta 1,000, I guess RE tau is 500-ish, and your roughness is maybe anywhere between 10% of the boundary layer thickness. So I think it's definitely a roughness, and my suggestion is, but mirroring the flow within the roughness sublayer is going to be challenging in experiments. So I do agree with you that you need some simulations to capture the physics there. And I think, again, I think you should look at the spatial variation. You can refer to my paper or Junlin's paper about how wake flow can be utilized to analyze the Reynolds stress budget and momentum transfer.
Oh, cool. I definitely will check the paper.
Okay, thank you.
Yeah, if any other questions? If no, let me ask a very naive question. So I saw like in your like say the rotationary flow, like you have like Reynolds stress like U prime V prime plus, and then you have the like U prime tilde and V prime tilde plus. So what is U prime tilde and U prime tilde plus?
Yeah, so that TLD is it's for the wake. Without that TLD is the stochastic Reynolds stress. That TLD is basically the spatial variation due to the geometry of the roughness elements.
Oh, okay.
Yeah,
so that's something I should check. What's the definition there?
Right. It's either called wake field or dispersive stress. Depends on the context the paper is focused on.
Oh. So okay, so if there's no questions, so I'll say like thanks again for Dr. Wu to give a presentation, and we'll see you next week.
Thank you all. Thank you for this opportunity. Bye.